Good afternoon, everyone. Thank you so much for joining me today. It's a great pleasure to showcase our research at the Work in Progress seminar. I look forward to learning your feedback. So my talk for today is titled Metabolic Signature of Ultra-Processed Food in Association with Colorectal Cancer Risk. So we know colorectal cancer remains one of the most common types of cancer and the second leading cause of cancer deaths in the US. It is strongly associated with suboptimal dietary intake, and among which the ultra-processed foods, or UPFs, which account for about 60% of Americans' daily calorie intake. It has been emerged as an important risk factor for CRC, the colorectal cancer. Ultra-processed foods are defined as formulations of ingredients and most of exclusive industrial use and typically created by series of industrial techniques and processing. So our previous research have shown that the high UPF intake was associated with a 29% higher colorectal cancer risk in US men, and 18% and 20% higher risk for advanced adenomas, and a 65% higher mortality caused by cardiovascular disease among stages 1 to 3 CRC survivors. Growing body of evidence suggests that the high UPF intake could negatively affect the CRC risk. However, the underlying mechanisms remain largely unsettled. The high UPF intake may increase CRC risk by introducing the carcinogens such as processed meat and unnatural soil compounds from food processing. Both randomized control trial and observational studies found that the high UPF intake is associated with weight gain, possibly leading to obesity, which is an established risk factor for 15 types of cancer, including CRC. Additionally, emerging evidence suggests that the food additives, including emulsifiers, artificial sweeteners, coloring agents, and nanoparticles, can also affect cancer risk and other GI disease by altering the gut microbial composition and the gut permeability, which can trigger inflammation through different pathways. All of these are closely related to the changes in metabolites. The metabolic alterations are considered as a major hallmark of cancer. Therefore, an understanding of the metabolomic responses to the UPF intake can help to decipher the underlying biological pathways that link the UPF to CRC. Emergent studies has already integrated the metabolomics to identify the potential biomarkers for colorectal cancer. And most of them conducted the univariate analysis of the candidate metabolites. And they only focused on or targeted on a specific class of metabolites. This approach could generate some useful information for certain metabolites, such as circulating lipids and some amino acids. However, it is less efficient and less informative as it relied on prior knowledge and also couldn't show the overall metabolomic responses. Additionally, it didn't account for the correlations between individual metabolites, which may pose the challenges in interpreting the study results. On the other hand, a few studies used a systematic approach to identify the metabolomic signature of dietary intake and evaluate their association with the CRC risk, but they only focused on the single food group, such as processed meats. The metabolomic profile of ultra-processed foods remain largely unknown and need to be characterized. Furthermore, the traditional dietary assessment of UPF intake, such as using the food frequency questionnaire or 24-hour dietary recalls, is prone to measurement or reporting errors, which could bias the estimated association between ultra-processed food intake and the disease outcomes. Therefore, it is critical to find a complementary method to assess the dietary intake. Advances in the high throughput profiling has shown great promise in subjectively measuring the dietary intake and identifying the metabolomic changes in relation to cancer risk. To address those knowledge gaps, we propose to integrate this technique with the epidemiological information to answer the following questions. The first one is, what are the metabolomic changes in association with ultra-processed food intake? And what is the association between the identified signature of UPFs and the colorectal cancer risk? Our study drew participants from two well-established cohorts, including the Nurses' Health Study and the Health Professional Follow-up Study. This figure provides an overview of the study design of these two cohorts. So briefly, the Nurse Health enrolled over 120,000 middle-aged female nurses starting in 1976. And the HPFS enrolled over 51,000 male health professionals who were 40 to 75 years old in 1986. The cohort participants completed the self-administered questionnaires regarding their medical conditions, family history, and the lifestyle factors every 2 years. They also completed the validated food frequency questionnaire every 4 years. The UPF intake was estimated using the food frequency questionnaire data starting in 1986. And then a subset of participants, including nearly 33,000 Nurse Health participants, provided blood samples between 1989 and 1990, and over 18,000 HPFS participants provided blood samples between the 1993 and the 1995. During decades of follow-ups, more than 3,800 CRC cases were documented. Using these blood samples, the metabolomic profiling data were generated using the liquid chromatography mass spectrometry method. There are now over 17,000 individuals with the metabolomics data available in our cohorts, including nearly 700 pairs of the colorectal cancer cases and controls. Of note, these CRC cases, they were documented after the blood draw. And also in our analysis, we estimated the UPF intake using the data collected from the FFQs that were administered at the time of blood collection. And our analysis includes two phases of data analysis. So the phase one is to develop and validate the metabolic signature of ultra-processed food intake. And then the phase two is to evaluate the association between the derived signature and the colorectal cancer risk. So in phase one, we used the metabolomic data as well as the dietary intake data from over 1,700 cases and controls of other disease in our cohorts as the training data set. Then we applied the elastic net regression with tenfold cross-validation to identify the UPF-related metabolites. And we generated the weight for each of them. After that, the metabolic signature of UPF intake was calculated as the weighted sum of the model selected metabolites with weights equal to the coefficients from the elastic net regression. We then validated the signature by using it to predict the UPF intake in the training set and also the CRC cases control pairs. The Spearman correlation analysis was performed to evaluate the validation. And then in phase 2, we applied the multivariable adjusted conditional logistic regression to estimate the odds ratio and 95% confidence intervals for the association of the signature as well as its component metabolites with the CRC risk. And the potential confounding factors include a wide range of demographic, medical, and also the lifestyle factors. Before we jump into the main results, let's first take a look at the distribution of UPF intake among our cohort participants. As we can see here, we estimated both the UPF intake as well as the intake of UPF subgroups as servings per day with energy adjusted. And the average intake for is 6.5 and 6.6 servings per day for men and women in our cohorts respectively. Each color block on this donut chart represents the contribution of a specific UPF subgroup to the total UPF intake. So from the two charts, we can see that the ultra-processed bread and the breakfast foods, as well as the fats and the sweets, as well as beverages, they contributed to the most intake of UPFs. Now let's dive into some details about the signature. So using the two-phase approach, we derived a metabolic signature of ultra-processed food intake. This signature consists of 39 individual metabolites. The bars represent the weights generated from the elastic neck regression. If a bar directing to the right side suggests a positive association with UPF intake, and if it direct to the left side suggests a negative association. Among all of those identified metabolites, we found 17 of them, they were positively and the 22 of them, they were inversely associated with the total UPF intake. Then this heat map shows the correlation between the plasma level of individual metabolites and the intake of the observed total UPF intake. So the red color indicates the positive correlation, while the blue color indicates the negative correlation. And we use the asterisk indicates the statistical significance of after adjusting for multiple comparison using the false discovery rate method. As we can see here, the magnitude and the direction are largely consistent with the weights generated from the elastic regression. Yeah, they are kind of speak to each other. And then this pie chart shows the composition of this metabolic signature of UPF. These metabolites belong to 10 subclasses, including the amino acid and the glycerol phospholipids, carnitines, ceramides, and other types of lipids and nucleotides. As we can see, majority of them, they are lipids and amino acids. The box plot here shows the distribution of the metabolic signature across quintiles of the observed total UPF intake. The correlation between this signature and the observed intake is 0.26, which is slightly low, but it is still within the range of dietary biomarkers reported in previous literature. This slide shows the association between the metabolic signature and the CRC risk. The x-axis shows the quintiles of this signature, and the squares indicate the estimated odds ratio with 95% confidence intervals showed by the vertical lines. Individuals in the highest quintile had a 52% higher CRC risk compared to the reference group. And when evaluating the association between the observed UPF intake and the CRC risk, we didn't observe any significant association here. Taking those two figures together, these results suggest that the metabolic signature of UPFs showed a better performance in predicting the CRC risk when comparing to the observed intake. And then this figure shows the association of CRC risk with the individual metabolites captured in the signature. We can see among of them, the N2 dimethylguanosine, which is a potential biomarker for meat intake, showed a strong positive association with the CRC risk. As we can see here, the odds ratio is about 1.56. And then the next one, which is the 21 dioxycortisol, which is associated with the cortisol biosynthesis. This one shows an inverse association with our CRC risk. Of note, we can see although majority of those associations, they are not significant. But as I highlighted in the red box and also the blue box is here, the direction of these associations is largely consistent with the direction of either the weights derived from the elastic regression model or the correlations with the observed intake. So we also considered the other demographic and lifestyle risk factors, considering they could be highly correlated with UPF intake. So the specificity of our signature might be limited. To address this concern, we further conducted stratification analysis. These results show there's no difference across this stratum. We also evaluated the correlations between the signature and these known risk factors for CRC and found that the correlations are fairly low. These results indicated the good specificity of this metabolic signature. In summary, our study identified a metabolic signature of ultra-processed food intake and associated the signature with CRC risk. Our signature, this signature and its components may serve as a biomarker for assessing the UPF intake. Our study findings also provide the biological insights into the potential metabolic pathways linking UPF to CRC. I would also highlight several strengths of our study. So this research integrated the high throughput metabolic profiling technique with the well-established large cohorts, which provides very comprehensive epidemiological data. And we also rigorously derived and validated the signature in both the training data set as well as the CRC cases control data sets. And also the comprehensive epi information from the two well-established cohorts allowed for the adjustment for a wide range of potential confounding. There are several limitations to acknowledge. In this study, we only include the named metabolites, and it is possible that we lose some information related to the unknown metabolites. And also the generalizability of this signature may be limited, as a majority of them, of our study participants, they are non-Hispanic whites and health professionals. And lastly, due to the nature of observational studies, we couldn't confirm the causality. As the next steps for the future direction, I think it would be interesting to evaluate the metabolic responses of the unknown or unnamed metabolites related to the UPF intake and the CRC risk. Also, a comprehensive literature review and also some future preclinical studies are warranted to have a better understanding of the underlying mechanisms. I'm also very interested in studying the interplay between UPF's gut microbiome, metabolites, and the CRC risk, as the emerging evidence has suggested the critical role of the gut microbiome in modulating the UPF and the CRC relationship. The gut microbiome research would provide some new insights into the potential biological pathways. And lastly, I would like to thank my mentors and the collaborators for their guidance and the contributions to this research. I'm very grateful for the support from my colleagues and from our department, especially for Dr. Albert Hoffman, Copelia, and Donald. Without the study participants and the staff from the 2 landmark cohorts and also the funding support, we couldn't have this work done. And also thank you all for your attention. I look forward to your comments and questions.